So dear colleagues, welcome in next colloquium of our faculty. So we have a distinguished guest, Professor Tomáš Jungwirth from Institute of Physics, Academy of Sciences. He's known for his work in antiferromagnetic spintronics. He studied at Charles University at Faculty of Mathematics and Physics, where he finished his Ph.D. in '97 in condensed matter physics. Then he spent a couple of years abroad for postdoctoral researchers in Indiana University and University of Texas. Then he came back to Czech Republic, to Institute of Physics, and as well he's a professor in the University of Nottingham in Great Britain, and he's the head of Department of Spintronics and Nanoelectronics at the Physics Institute. And yeah, his work is seminal and I think very important, and that's why we invited him. I think he's in the forefront of material science, and we are happy that also he's one of the successful applicants for ERC grants. So he has already second ERC advanced grant, which is I think is for us, let's say, okay, let's say for young generation as a role model. So so we will be streaming this talk. So for the questions, I will pass you this animal. You will just because to be heard in stream. And now I will give a word to Tomáš. Please go ahead and tell us some news. Thank you.
Thank you. Thank you very much for the introduction and for the invitation. And thank you guys for having me and for coming today in the afternoon. So I will talk today, and I guess I will need to use this. Let me see. Can't see it. So I will talk today about ultramagnetism, and I will try to introduce to you this this new magnetic phase of matter. We started, seeing hints, theoretical hints that magnetism might be richer than what we thought before, and that there might be a new type of phase around 5 years ago. And then a couple of years later, we rigorously delineated or defined, based on symmetry, this magnetic phase that we now call ultramagnetism. And last year, we together with our colleagues across Europe, we made first experimental observation, direct experimental observation of this phase. And this made it to this end of the year issue of Science of the breakthroughs of 2024. And ultramagnetism was chosen to represent physics among all sciences that are part of this list. Now, I believe the reason why ultramagnetism was chosen to represent physics is that it is believed now that it may have many consequences in a broad range of fields across physics. But there is no way that, within the 45 minutes, how long you guys will be keen to stay today, I could introduce all this broad research context that is now emerging in connection with ultramagnetism. So instead, I will focus on one specific research context, and that is information technology, or the physics of information technology. First of all, because I want to focus it, but maybe more importantly, because information technology was one of the key incentives that actually led us to the identification of this phase. And I also think that by looking at ultramagnetism from this perspective, I can just introduce the concept without having to go into too many technical details, equations, or data. I hope it will allow me to just to stay on a conceptual level, and the field of information technologies hopefully can facilitate this. So let's see if it works or not. So IT, or information technology, as in my view and in view of many people around, is actually now undergoing a revolution in terms of physics or materials underpinning the technology. And this is because it's the first time in history where semiconductor memory bits on a processor chips are actually being replaced with a completely new technology. This is the first time in the entire history of integrated circuits that we have now bits which are not made of semiconductors. Now the technology is called spintronics, and it's based on magnetism. So, so let me introduce that. Now, magnets are actually not new to information technology and to technology for representing the logical zeros and one in bits. Magnetic bits were actually running the computer that was behind the Manhattan Project. So it was a magnetic relay, and it was a magnetic relay, which as you very well know, is a classical magnetic device in which when you apply current through this magnetic coil, it will raise this magnetic arm, and it will open the circuit. That means current cannot flow, and if you want to represent it by a bulb, there will be no light. If you then switch off the electrical current through the coil, the magnetic arm goes back to the original position. It connects, closes the circuit, current can flow, and bulbs, the light bulb is shining, and we have logic 1. So this was the digital bit in the Manhattan's Project computer at the end of the Second World War. And it has two enabling features which simultaneously are the main limiting features of this in light of the future developments of information technology, integrated circuits, etc. And the two key features is that we have, first of all, magnetic stray fields. And you don't want to have magnetic stray fields in your integrated circuits because they are, in principle, long range. And you can have unintentional crosstalk between the bits. And the second is that you have physically moving parts in the bit. And if you now imagine that your bits are switching a billion times a second in a processor chips, it's unimaginable that you would have a mechanical part representing your bit. So from that perspective, the discovery or invention of the transresistor effect and the corresponding transistor was really completely groundbreaking at the time. It's basically the very same time. The discovery is right at the end of the Second World War. And what is in transistor is that we actually remove both the magnetic field and the physically moving parts in our switch, which is turning on and off this electrical circuit. So in transistor, as you very well know, we instead apply electric bias on the central electrode, and this electrical bias either moves electrons out or in the conduction channel. So we are not physically moving anything, but we're just moving electrons in and out the channel by electrostatic gating instead of magnetic field. And this then can represent the logic 0 and 1. So this was, first of all, a physics discovery, because it was one of the first victories of quantum mechanics, understanding how semiconductors works, because you can do this only in semiconductors with something for which we required the knowledge of quantum mechanics. And indeed, Bardeen and Breton and Shockley were physicists. I mean, Bardeen, in fact, received a Nobel Prize not only for the discovery of transistor, but later on even for discovery of, or theoretical explanation of superconductivity. It's the only physicist with 2 Nobel Prizes in physics. Now, Shockley was a physicist, but he was also an entrepreneur. And as you know, Shockley, shortly after the discovery of transistor, moved to California, and he physically started the Silicon Valley. Now, always when I look at these 3 folks, then I'm thinking, what the poor Breton must be thinking, right, with just 1 Nobel Prize. Like a big underachiever compared to his 2 colleagues. And that brings me to the spintronic bits that we want to talk about today. Now, spintronic bits are, surprise, magnetic. So magnetism is coming back to information technology, but in a completely different reincarnation. In spintronic bit, we do not have any physically moving parts, and we do not operate the bit with any externally generated magnetic field. So the magnetic field is not needed for the operation. There's no moving parts, physically moving parts, and we are not even removing the electrons from our conduction channel or from the device back and forth through the channel. The electrons are still remaining in the channel. Nothing is moving in and out. What we are doing is something different. The spintronic bit comprises 2 magnetic electrodes, and the logic 0 and 1 state correspond to an opposite magnetization of the 2 electrodes or the same magnetization of the 2 electrodes. And now when the 2 electrodes are magnetized in parallel, electrons that carry electrical current through the bit, the magnetization is copied on their spins, on the elementary magnetic moment that every electron carries, which is spin. So the magnetization is copied, and when the magnetization is the same on the other electrode, electrons have a very easy time to actually go through that device and can carry electrical current. However, if the magnetization is opposite, the electrons with their spins have a very hard time to cross this junction, and there's virtually no current flowing. Again, this is both a physics discovery. It was awarded another Nobel Prize, but as we will see, it also has a major technological consequences. The consequences are that as of today, and this is really new. I mean, this is something which is not more than 2 years old news. Although, of course, the companies must have been intensely working on this over the past decade, is that now these bits start to replace embedded flash bits or embedded static random access memory bits on the microprocessor or on the microcontroller chip. So we're talking about memories that are not standalone, but are on chip, on the microprocessor chip. And the reason why they start replacing is not that the semiconductor industry is particularly in love with magnets compared to semiconductors, but it's simply because flash is becoming prohibitively costly when you go below 20 nanometers node. It's just impossible money-wise to keep on fabricating these flash memory bits. And SRAM is becoming leaky. At these small dimensions, they are unable to close sufficiently the channel by the electrostatic gate. While this magnetoresistive or spintronic memory bits still can very well operate under the 12 nanometers. And in fact, it's not just one company, but it's all the major players in the semiconductor industry, all the foundries, including Global Foundries, Samsung, or TSMC, which are now starting to replace eFlash and eSRAM with these embedded magnetic random access memories. So this was the technology. Now let me take a look at the physics in more detail of these magnetic random access memories And based on this, it will lead us to what are the basic physical limitations of this technology, understanding of how altermagnets are different from the conventional magnets that we use in the commercial magnetic random access memories, and what is their physical principle and how they can possibly overcome the limitations of the conventional magnets. So let me start with the conventional one, that means with ferromagnets. And let me take a look at ferromagnets from the physics perspective. What is ferromagnetism? Now, ferromagnetism is an ordered phase, and by ordered phase, what we mean is it's a phase that spontaneously breaks symmetry of the Hamiltonian of the system. So it's a state of matter which has lower symmetry than the interactions that are defining the properties of the matter. And the specific interaction, which is critically important for the formation of these ordered phases, like ferromagnetism, is the electron-electron Coulomb interaction. So this is a term in Hamiltonian, which, as you see, has no explicit spin dependence. And because it has no explicit spin dependence, this interaction term, or the corresponding Hamiltonian, has spin rotation symmetry. I can do any spin rotation transformation, and nothing changes with this interaction term in the Hamiltonian. So the interaction has spin rotation symmetry. Now, we talk about a normal phase, a normal non-magnetic phase of a system, when the phase also has the spin rotation symmetry. So in the normal phase, when I look in the direct position space, I have a piece of material, and I don't see any spin polarization, any spin dependence. So I can rotate the spin space whichever way I want, nothing changes. And the same applies in the momentum space when I look at the energy spectrum, or specifically when I look at the Fermi surface. The Fermi surface is spin degenerate. There is no spin dependence. I can rotate spin whichever way I want, nothing changes, so it's symmetry. Now, in the ferromagnetically ordered phase, this is what happens. The ferromagnetic ordering is due to the same electron-electron interaction term, which still has no dependence on spin. It's still fully spin rotation invariant. However, when you look now at the ground state, it breaks the symmetry. So the ground state spontaneously decides to break the symmetry of the underlying Hamiltonian. Because now I have in my direct space, I have magnetization, which is pointing up. And in the momentum space, I have a majority Fermi surface of spin-up electrons and minority Fermi surface of spin-down electrons. If I rotate spins, I get a completely different state. I have a state which is magnetization pointing down, and now I have majority Fermi surface with spins pointing down. So these two states are not different. They break the spin rotation symmetry, but they break it spontaneously in the ferromagnetic state because the symmetry is not broken in the interaction, which is responsible for this ferromagnetic ordering. Fine, we have two different states, and those can then represent the two logic states, 0 and 1. Now the question is, when we talk about information technology, microelectronic devices, integrated circuits, is how in the world am I going to distinguish these two states electrically? What I see is a complete difference in the spin space. Here I have majority blue, here I have majority red, the opposite spins. But when I look at the shape of the Fermi surface, it's identical. The orbital part is completely identical. So if you run electrical currents through a ferromagnet in this state or in that state, it will be exactly the same. So how in the world am I going to electrically distinguish this? Well, that's the genius discovery or invention of Wirth and Greenberg, who were later awarded by the Nobel Prize, of this magnetoresistive, or specifically giant magnetoresistance effect. So what these two guys did is they said, fine, I have my magnet, which can be in these two states, magnetization up or magnetization down, representing logic 0 and 1. And I will make a device which will have another magnetic electrode. And in this case, the magnetization of this so-called reference electron will stay fixed. It will be always pointing up. Now, when I now look at the respective Fermi surfaces, I have a perfect correspondence in this case. So I have a majority spin up on either side of the junction, while in this case, I have majority spin up, while on the other side of the junction, I have majority spin pointing down. And that's a problem. If electrons now want to cross in this scenario, the electron could only cross from this Fermi surface to this Fermi surface when carrying the electric current only upon flipping the spin. Without spin flip, it's not possible. So it's really happening in the spin. The fact that suddenly electrical current can flow in this case, but cannot flow through the device in this case. It's an electronic response. It's resistance. But the resistance is directly measuring what is happening in the spin space, which is separate from the orbital space. I think it does deserve a Nobel Prize. Now, fine, you may think, okay, I can read. I can electrically distinguish the two states, in one case large current, in the other case small current. But I also mentioned that I don't need any magnetic field to operate this device. And now you think, okay, how am I going to switch it? How am I going to switch the bit from 0 to 1, magnetization up to down, electrically? This is readout, but I'm talking about writing. How am I going to switch it? Well, it took other two guys. They didn't get the Nobel Prize yet, but they got the highest American Physical Society prize, not bad, as a start. What these guys did, or suggested, is just do one thing. Just add another battery, meaning apply a higher bias across this junction. Apply a higher voltage across this junction, such that now these electrons actually can be pushed through the junction to the other side. And if you succeed in pushing enough spin-up electrons into this electrode, it will actually make spin-up electrons majority, and it will flip the magnetization. So it's pure electrical. I'm not using any magnetic field. I'm just pushing electrically electrons with their spin from one side to the other, and eventually they will turn the magnetization upside down. If you're wondering how do you switch this back, well, you just rotate the bias, you reverse the bias, and now it will be these electrons moving from the upper electrode to the bottom electrode. And once you removed enough spin-up electrons from the top electrodes, the spin-down electrons will take over, and they will flip the magnetization back. Okay, so this was good enough to have a device which you can electrically read and electrically write. By the way, the dimensions of these electrodes are just a few nanometers in thickness, to make it a viable technology for the semiconductor industry. But there are still some buts. I said we don't need magnetic field to operate this device. But my electrodes are still magnetic. They are permanent magnets, and they are generating their own magnetic field, whether we like it or not. We don't need it for anything. It's just a nuisance now, but it's still there. And that does limit the density of integration. And actually, the engineers who are fabricating these integrated circuits, this is their key concern. The stray fields, how to go around the problem of stray fields and having still dense enough memories is the key problem. The other one, or the other limitation, is that with ferromagnets, we know, this is the physical limit, that the maximum speed at which you can switch the magnetization from up and down is about a nanosecond time scale. This is the shortest, or in terms of speed or frequency is gigahertz. Without requiring an excessively large energy or huge currents, you are limited by the gigahertz frequency. As long as you are below gigahertz frequency, megahertz something, it still takes about the same energy. But if you want to go beyond that, it will be impossibly energy hungry. And that's the very physical nature of ferromagnets, which, for the moment, may not be a critical problem because the processors themselves, they also work at gigahertz frequency. That's why these can be compatible. But there was a guy at IBM already in 1961 who was looking at bits and integrated circuits from the fundamental thermodynamic physical principle. And what he found out is that the fastest and simultaneously least dissipative switching of any physical bit, doesn't matter what is the physical realization, is in terahertz or in the picosecond time scale. You cannot, so there is still 3 orders of magnitude. If we could do, instead of gigahertz, if we could do it in terahertz, or if we can switch it in 1 picosecond, this is the physical limit of the fastest and simultaneously least dissipative switching for any bit. So it would be very nice to have a technology that allows us to go from gigahertz to terahertz. But ferromagnets, from fundamental physics point of view, they cannot deliver this. So magnetization in ferromagnets is a problem. Can we have another phase, another ordered phase, which has no magnetization? Again, generated by this electron-electron interaction? And the answer is yes. It was actually a physics field which was developed at the very same time or similar time to the main developments in spintronics, and the field is called electronic nematics. It's a very different type of order. It's due to electron-electron interaction, and now I like to point your attention that this interaction is not only spin-independent, but it's also isotropic. So if you have a bunch of electrons that are mutually interacting through the Coulomb interaction, in the normal phase, the Fermi surface that they would form will be isotropic, because the electron-electron interaction is isotropic. But there is an ordered phase, which is called nematic, in which case the electronic system spontaneously develops an anisotropic deformation of the Fermi surface. Now, in this case, this is all happening in the charge or in the orbital channel. You can imagine measuring electrical current along 2 different directions, and they will be different, because I have anisotropically distorted my Fermi surface. So resistivity along this direction and this direction will be spontaneously different when the system is ordered in this nematic phase. Now, based on this principle, you can imagine that I can also represent the logic 0s and 1. If I can figure out some knob by which I will define whether my Fermi surface would squeeze in this direction or in that direction in the ordered phase, one could represent logic 0 and one could represent logic 1, and I can read the state by different resistivities when running the electrical current along the same circuit. Now, first of all, it's not very easy to imagine what kind of external knob I can use to actually choose which of the states will form in the ordered phase. But it's sort of least of a problem when talking about this phase. Because ferromagnetism, we know, can occur in systems like cobalt, iron, transition metals. They are actually ordering at room temperature, and we know very well that the ordering mechanism is very robust. It's this electron-electron interaction combined with the Pauli exclusion principle, and this is what we call exchange mechanism. And this can be very robust. It can work easily at room temperature. Here, we actually don't really understand very well what kind of electron-electron interaction mechanism can lead to such a phase. We suspect that it's some sort of a strongly correlated mechanism. And there are only few systems where this phase is suspected to be occurring. It's not even unambiguously proven. And one of the cases are 2-dimensional electron gas at very low temperatures and actually at very high fields. Oh, we did not get rid of the field if we talk about this system. We have to introduce it again to form such a phase. So this phase is really a no-go. And that brings me to altermagnetism. So what is altermagnetism? Altermagnetism is an unconventional spin-ordered phase in the sense that it, of course, spontaneously breaks the spin rotation symmetry just like a ferromagnet, just like a conventional ferromagnet, but simultaneously, it also spontaneously breaks the real space rotation symmetry. It develops a spontaneous anisotropy in perfect analogy to the nematic phase. So let me first represent this or show this on a cartoon level in the direct space, in the position space. So what do I mean? I have a magnetically ordered state where all my spins are lying along one axis. The difference from ferromagnets, though, is that half of the spins is pointing up and half of the spins is pointing down. But they're all aligned. Now I can then flip all spins, and instead of having an order up-down, I will have order down-up. There are two different states. I break spin rotation symmetry. They can represent 0 and 1. Fine. Now you were thinking, OK, that's nice, but electrically, I'm not going to generate spin polarized currents. This is what I need to do in any electrical operation. I need to have spin polarized current. The current is not going to be spin polarized because I have the same number of spin up and spin down electrons, right? Wrong. I run electrical current in an ultramagnet, and it is spin polarized. In this case, it's polarized up, and in this case, it's polarized down. And now you're asking the question, what the hell are these other half of electrons doing? Why is the other half of electrons not contributing? And the answer is in this spontaneous real space rotation symmetry breaking, or in this spontaneous anisotropy. And we will see it in this experiment. When we put our state of the ultramagnet into the same 0 state, that means is the up-down order in both cases. But now I'm going to run electrical current along this axis and along these axes, which in the real space of the crystal, imagine I have a cubic crystal, are absolutely identical. There is no difference between those two current directions. But in the ultramagnetic phase, this is what happens. In one case, the electrical current is polarized up, and in the other case, the electrical current is polarized down. This is where the other half of electrons was hiding. It was actually happy to carry the electrical current in this direction, but unhappy in this direction, and vice versa for the opposite spin. And this is happening all spontaneously in the ordered phase because the crystal itself is completely cubic symmetric. Now, if you now wonder what happens in a diagonal current direction, you now have electrical current as you would normally expect, which is spin unpolarized because it will be carried equally by spin up and spin down electrons. So this is the cartoon real space representation. Now the cartoon momentum space representation of the Fermi surface. This is the normal state. And what happens in the ordered state is this. So spin up Fermi surface is nematically like deformed in an isotropic way. And the spin down is also deformed, but the deformation is mutually rotated by 90 degrees. And as a result, I also have spin splitting. I also have spin polarization. This is the direct experimental observation of such a phase in real materials. And the real material is either manganese telluride, chromium antimony, and there are a few other materials in which there's been also a direct observation of this type of magnetic ordering. And what I want to emphasize here is that these are not kind of obscure materials, complicated compounds, something that people had to artificially synthesize or didn't know of. These are very simple binary compounds where people have had in their drawers for decades, including us, I have to admit, without knowing anything about them. And they also order at room temperature, which also tells you that the ultramagnetic ordering can be robust. So what you see here is the energy spectrum measured by angle-resolved photoemission spectroscopy. And this type of Fermi surface would correspond to this Fermi energy cut along the kx, going from blue, red, red, blue. It's exactly the same line, blue, red, red, blue. So it's different materials than the ferromagnetic ones, and certainly different materials than where we think we may have this nematic phase, which also means that the microscopic mechanism must be different. And it's also robust. That also tells you that it must be very different from the nematic one, which is very subtle and we don't even know if it exists. And the answer to this is that we know exactly what is the microscopic mechanism. It's a combination or interplay of the electron-electron exchange mechanism, the same as in ferromagnets, but in combination with the interaction of electrons with the single particle crystal potential of the lattice. These two conspire in the formation of this robust altermagnetic phase. And because crystal potential is so important for the phase, if we want to understand, we need to look microscopically of what's going on in that crystal lattice. There are about 300 identified altermagnetic materials in many different types of crystal lattices. What I'm going to show here is arguably the simplest model representation, but such lattice does exist in nature. So it's not a thought or an artificial model. It's a real model of altermagnetism and arguably the simplest. So I have ions in my crystal lattice. And what you see here is a cubic lattice, right? Now, let me add the electronic orbitals on top of these ions in the normal phase. And they respect the symmetry of my cubic or square lattice. So what you see here is that, for example, these orbitals have neighboring atoms in the horizontal direction, so I have higher electronic density here and lower in the vertical direction. These orbitals, or these atoms, have neighboring atoms in the vertical direction, so they have higher electronic density here and lower here. But overall, as a crystal, it still keeps the cubic symmetry. If you're not convinced, let me just rotate it by 90 degrees, and you would not recognize any difference. So the crystal has a perfect cubic symmetry, as is the cubic symmetry of my underlying crystal potential in the Hamiltonian. This is the normal phase. And the same applies to the electronic structure in the momentum space. Now, let me move to the altermagnetically ordered phase. So this is what happens. Spontaneously, there is spin ordering, but what happens is these guys, which have the horizontal neighbors, are going to be dominantly red, that means spin down electrons, while these sites, which have the vertical neighbors, will be primarily spin up, or the blue electrons. So obviously, my phase now breaks spin rotation symmetry, because spin rotation would flip blue and red colors, and the picture would look different. Now, how about the real space rotation symmetry? You already probably see that it's also broken, but let me do this explicitly. Instead of having the red ones after a 90-degree rotation, I have the blue ones on top. And the same, of course, happens with the electronic structure. So it's a phase that simultaneously breaks the spin space and the real space rotation symmetry. But as you see, a very important role was the symmetry of the ionic crystal lattice to generate such a spontaneously broken ordered phase. Now, if you wonder whether in condensed matter physics we have any precedence of such a phase, is there a phase which would spontaneously break both the spin space and real space rotation symmetry? Then the answer is yes. There is a very well established, but also arguably singular precedence, and that is helium-3. Helium-3 is a fluid of helium-3 isotopes, which, as you know, are spin 1/2, so they're fermions, like electrons. The only difference is that they have no charge, unlike electrons. But the important thing is that they're spin 1/2, so they're fermions, like electrons. And that means that they have Fermi surface. And in the normal phase, because they are not on a lattice, they're just free fluids, it will be isotropic or spherically symmetric. Now, what happens in the superfluid phase is this. In the superfluid phase, there is an order parameter, which is a vector in the spin space, which becomes anisotropic. And this vector order parameter is what defines the superfluid gap, which, as you see, is also anisotropic, developing these two nodes here. So there is a spontaneous real space rotation symmetry breaking, and there is also a spontaneous spin space rotation symmetry breaking because the order parameter is an aligned vector in the spin space. Now, when you compare it to our case, I mean, this is not really a magnet, though, right? I mean, it breaks the same symmetries. It breaks the spin space and real space rotation symmetries, but these arrows are not spin polarizations of electrons or fermions, or not magnetization. They are some vectors representing some vector order parameter in the spin space. If we had more time, we can exactly write down what kind of order parameter it is, but it's not just a spin polarization or magnetization. So it's a different type of, it's not certainly a magnet. But the other thing that I'd like to emphasize is that this is a very subtle phase. It can only be stabilized at 2 millikelvin, 30 bar pressure. And the reason for this is, the primary reason for this in comparison to altermagnets is that there is no lattice. There is no this strong lattice crystal potential that in case of altermagnets hold this unconventional phase together. It's just a fluid, and electron-electron interaction and some subtle correlations have to do both. They have to align the spin order parameter and simultaneously make the phase anisotropic. It is a very subtle mechanism, and as a result, also stabilizing this phase is very hard, and it requires extreme conditions. So that brings me to the last slide. What about now the comparison between the ferromagnetic and altermagnetic spintronics prospects? Where are we at, and what is the possible outlook? So we said that the key limiting factors of the current spintronics based on ferromagnets are the magnetic stray fields and the gigahertz frequencies. In magnets with zero net magnetization, we have already demonstrated on the level of discrete bits that we can operate them electrically, both reading and writing. They generate zero stray fields, and we can switch them by pulses, electrical, optical, scale down all the way to picoseconds or even sub-picoseconds without any excessive increase in switching energy. So that has been demonstrated already. But we also know that for the successful operation of these devices, we need to have these spin polarized currents. This is something that we already also demonstrated in ultramagnets. We already know and experimentally demonstrated that if we run electrical currents, they will be spin polarized in ultramagnets. But the critical thing in ferromagnetic spintronics was not just that we have spin polarized current in one magnetic electrode, but that we can build this so-called spin valve device, that we can have this multi-layer stack in which we can block the electrical current depending on the orientations of the spins on the two respective electrodes. This is something which has been theoretically predicted to work equally well in ultramagnets, but on the experimental side, this is still on the to-do list. It has to be demonstrated, and the key thing is the size of this magnetoresistance effect. If it's only a few percent, it's not going to make it to commercial applications. Here in ferromagnets, we have 200% effects at room temperature, and this is what is needed. That still is yet to be demonstrated in ultramagnets. If we have this, we're definitely not immediately commercial, because there is so many more things that have to be shown on the engineering side that you can take this device and integrate it on the semiconductor wafer or on the semiconductor-based integrated circuits. It's the materials compatibility, the way how you integrate these bits into the very complicated structure of these integrated circuits is an engineering issue which has been the major reason why in ferromagnets it actually took more than 2 decades, nearly 3 decades, to make it from the original discovery to applications. Whether something like this would be possible with the compensated magnets like altermagnets is certainly at this point a completely open question. So thank you very much.
Thank you very much for the presentation. So now we have place for questions. And so, Marek, I have to sort of
Thank
speak to the place.
Thank you very much for a very nice talk. I was wondering what would be your conception, what was the main bottleneck for this effect to be observed earlier? You were saying that it's quite robust, it exists at room temperature. You were mentioning 300 compounds that exist that have this. So if you have spin preference of the electrical current flowing out of the chip, what was the main issue? Why hasn't this been observed 10, 20 years ago?
Well, let me start answering your question by asking a simple question. I tried to explain what altermagnetism is to you guys using no equations, no quantum mechanics expressions, no detailed data, just on cartoon level, right? Just using the basic notions, let's say basic textbook notions of quantum condensed matter physics, but without even going into any details, any detailed expression. Do you feel that you can understand what altermagnetism is based on this? If the answer is yes, then it tells us that actually this could have been easily discovered in the 1930s. And I would fully agree with that. In 1930s, they had all the conceptual understanding of physics that they could completely understand the existence of altermagnetism. So we can ask, it's more philosophical than I guess maybe scientific question, why in the world is it discovered only now? And I have a few tentative, suggestive, if you want, answers to this. So one is Louis Néel. Louis Néel is credited for discovering and describing, in particular, describing antiferromagnets. So these are systems which has also compensated antiparallel moments in the crystal. And Louis Néel made this discovery in the 1930s, Nobel Prize 1970. And still in this Nobel lecture, he is explicitly saying that, first of all, antiferromagnets are useless. He's saying explicitly, or they have no practical application. And he is explicitly saying that there will be no phenomena like in ferromagnets which depend on switching the spins. He's saying I can have the same effects as in ferromagnets, which are quadratic in magnetization or quadratic in the sublattice magnetization. These are relativistic effects. If you include relativistic spin-orbit coupling, your spins are pointing in this direction in crystal or in a different direction of crystal. You can have slightly different energy, relativistic energy. This effect will be equally present in ferromagnets or antiferromagnets because it's quadratic in the local magnetization. But just by flipping the spins by 180 degrees, you have no effect in antiferromagnets. This is how people perceive these compensated magnets throughout the century. It's been encoded. It's been simply a common understanding. This is it. This is how physics works. So people were not looking. If you know that something doesn't exist, you don't look. We had manganese telluride, and we even published papers in 2016 where we are showing that this is a perfect antiferromagnet, which exactly agrees with this Néel's picture of antiferromagnets. And only when you completely change your mindset and you start thinking, oh, maybe there will be this spin polarized effect, you redo the same experiments, you remove all additional artifacts that are in the data, you clean up the data, and you suddenly see clearly that the signal is there. But if you know in advance that it's not there, you're not going to do this. You're not going to put this extra effort into your experimental analysis. This one, and I think maybe the more important is that, for example, in this ARPAS measurement, when people do ARPAS, I'm going in the wrong direction. Let me just put. Where am I going to do? Looking for some nice ARPAS data later on in my slides. For example, here. So when people, so this is a Fermi surface of a very nice altermagnet, which is exactly the same crystal structure compared to the model one. And so it is almost in textbooks of how you do DFT calculations, how you do angular result photoemission when you want to understand spectra of your material is. You just look at high symmetry planes, high symmetry lines, high symmetry points in your Brillouin zone. There are standard procedures that people were following for decades and decades. How am I going to do this spectroscopy measurements and corresponding density function theory calculation? Go along the high symmetry planes, go along the high symmetry lines and high symmetry points, see what you see. Because the sign of the spin polarization alternates in altermagnets, there have to be points, there are actually planes which are spin degenerate. And they, no surprise, are the high symmetry planes or lines or points in the Brillouin zone. So there are many ARPAS data on many materials which we now know are altermagnets, including, for example, the parent cuprate of high temperature superconductivity, which has been extensively studied by DFT and ARPAS. And there are papers from 2019 showing all these high symmetry planes and lines which are spin degenerate, and they have to be by symmetry. But if you would go away to a general momentum, you will open a spin splitting, which can be electron volt large as the splitting at the gamma point of a ferromagnet. This is another answer to your question. One more answer is that you cannot distinguish by the standard symmetry nomenclature, which is the so-called magnetic groups. You cannot distinguish in most cases a ferromagnet from an altermagnet, because they would both belong to the same magnetic group, magnetic symmetry group. The problem there is that the standard, what has become a standard, are magnetic groups which are relativistic. So they only allow for symmetry transformation where you do the same symmetry transformation in the spin space and in the real space simultaneously, because you have spin-orbit coupled system, relativistic, and of course then spin and orbitals live in the same reference frame. So you always do this, you only allow for the same transformations. And if you only allow for the same transformations, your landscape of symmetries that you consider is very limited. Now, if you only want to look at the magnetic ordering, which is due to the electron-electron interaction term, there's no spin. So there's no coupling between spin and real space. If you talk about physics due to the electron-electron interaction, you should use different formalism of symmetries. And that's a formalism which allows for different rotation transformation in the spin space and in the real space. So what I was showing you all the time was a symmetry transformation which was 90 degree in the real space combined with 180 degree in the spin space. That symmetry transformation does not exist in magnetic groups, which is the basis of symmetry description of magnets in the crystallography endorsed textbook by the International Union of Crystallography as of today. This symmetry transformation is not allowed. It doesn't exist. Although there were physicists in the 1970s who developed the complete formalism of the so-called non-relativistic spin symmetries, where you allow for different transformations to be applied in the spin space and real space. We did not develop this formalism. We took the formalism from the 70s, but it was never applied to systematically understand the type of phases you can have in magnets. So this is what we did. And suddenly you see that the richness of the phase space that you can have in magnets is much higher because you have much richer toolbox of symmetries. Of course, ultimately, all systems are relativistic, but the point is that the ordering is dictated by the non-relativistic spin symmetries. The relativistic symmetries can induce some small changes in your electronic structure, open a small gap here, maybe some small non-collinearity or something, but overall, the type of phase you have is determined by the non-relativistic electron-electron interaction.
Thank you.
Is that a partial answer to your question? Yeah.
Very much. Thank you very much. Let's keep looking.
Next questions or comments? So maybe first we talk to there and then to the okay.
So I would like to ask if it's possible to have altermagnetism in some material which does not have the cube symmetry.
Perfect. Yes. Thanks for the question. So the most general definition of altermagnetism is that is a system which has a symmetry that combines the two-fold spin space rotation or 180-degree spin space rotation with any crystallographically allowed rotation in the real space, okay? And we know that crystallography does not allow for any rotation. It allows for two-fold, three-fold, four-fold, and six-fold. And among all these, you can have altermagnets, and they will be different. So you can have altermagnets which look like this, which basically have only two, the so-called nodal or spin-degenerate Fermi surfaces, and the symmetry corresponds to d orbitals. So we call this d-wave ultramagnets. In analogy to d-wave superconductors, it's all the same type of symmetry. Now, in other types of crystals, you can have four nodal surfaces, which would correspond to what is in atomic physics called G-wave. We don't know much G-wave. We typically end with F-wave because G-wave are not typically occupied orbitals in atoms. But it's the angular momentum L equals 4 spherical harmonic. And you can have also I-wave, which is the L equals 6. So you can have D, G, or I, or 2, 4, or 6 nodal surfaces, depending on the crystal structure, which can be other than cubic, it can be hexagonal. For example, this manganese telluride crystal is actually a hexagonal crystal. And it's also a perfect altermagnet. So you can have others, and depending on the specific crystal structure, you can have this D, G, or I wave, but it's always even parity.
So I should talk to the face? Yes. Okay. One of the possible application of these processes are in computer engineering, basically, to increase computing capacity of the computers, if I understand this correctly. But there are some other processes which are also, at least in theory, very fast, with similar physical limit, about 10 picoseconds, and these are scintillation processes in some crystals. Do you think these processes can be also used for computing, or are you interested in these processes?
No. This is a perfect challenging question, which I was never given before, and I was never thinking about whether we can have a. If the question is whether we can have an altermagnetic or even a magnetic scintillator, that means a transducer of some radiation into an optical signal. As far as I know, all the existing scintillators are non-magnetic, but prove me if I'm wrong. And I am not sure whether magnetism could be of any help. So, you know, I'm not gonna twist my or your arms here. I don't know the answer.
Okay, so other question? Okay. Okay, so then I have to throw it back, sorry.
Thanks. Maybe a naive question. If you mentioned the effect of temperature, so something like Néel temperature in antiferromagnetism, I suppose that is the same thing. And this transformation, could it be via, for example, from altermagnetism to antiferromagnetism, and is it straight or via some intermediate?
Yes, thank you for the question. So the answer is yes, and there are papers published on a transformation from an altermagnet to a now we first have to define what we mean by antiferromagnet to this other phase and vice versa. So what we mean by, let's say, Néel antiferromagnet is a phase which is also collinear. It's also perfectly compensated. The compensation is by symmetry. But if you look into the electronic structure, it's completely spin degenerate. So you would not see the difference between a non-magnetic phase and the Néel antiferromagnetic phase if you would just go to the electronic structure, momentum space, in terms of spin polarization. The bands can be different, but they will not be spin polarized. Now, what is then the difference the basic difference in symmetry is that in these conventional Néel antiferromagnets, and this is also what Néel has always imagined in his seminal papers or later on in books and review articles is that in this Nail antiferromagnet, you have the opposite spins in the crystal connected by a translation symmetry transformation, okay? And what I will now say would equally apply if the opposite spins were connected by inversion in the lattice. So if you had such a symmetry, then this symmetry dictates that in the momentum space, you will have completely spin-degenerate electronic structure. Now, if I not talk about relativistic spin-orbit coupling, okay? For the translation, relativistic spin-orbit coupling at some circumstances can introduce spin splitting, but it would be the same as in non-magnetic system. The magnetic ordering does not introduce any spin splitting if the opposite spins are related by translation or by inversion. So what you need to have such a transition is to have crystal where, for example, you have one spin and the opposite spin, and the crystal lattice environment, the other non-magnetic atoms in the lattice, are somehow mutually rotated. Okay? So that there is a rotation transformation from one to the other, which connects the opposite spin sites. If you have that, it's an ultramagnet, and you simultaneously do not have the translation because the environments are mutually rotated. So you don't have the translation, and you also don't have the inversion. But if you, by, for example, applying strain or something else to the crystal, you would make these local environments sort of straighten up. So if you can manipulate those local environments from mutually rotated to mutually parallel, and therefore introducing a translation symmetry transformation between them, you can turn on and off the spin polarization in the electronic structure, and you can turn on and off the altermagnetic phase, or switch it from altermagnetic to the conventional Nail antiferromagnetic back and forth. So this is one example.
Thank you. So next question. So maybe just I will. Okay, so still we have a little time. So experimentally, so how actually you measure these effects? So when you speak about the crystals, and you mention that it's like nanoscale, or is it macroscopic scale? How do you these materials? So how do you actually prepare them, and how do you measure them? So like physically.
So this is a real picture of the materials. Incidentally, on this slide, you can prepare them in bulk by all possible bulk synthesis techniques of materials. The bulk materials tend to be the best quality, but not the most useful for making devices. Therefore, people also like to prepare thin film versions of these materials. All spintronic devices are based on thin film ferromagnets, so you need to be able to develop a thin film, high quality thin film synthesis of these materials. So this is manganese telluride grown by our colleagues in Nottingham by molecular beam epitaxy, which is arguably the most sophisticated method for growing thin films. It's grown on a indium phosphide 3,5 substrate, and this is not just an accidental choice of a transmission electron microscopy small part of the wafer, but actually it's across the entire wafer. It's defect-free. These guys can grow films which are 30 nanometers thick, 5 by 5 millimeter chips, which have 0 defects. Okay, pretty impressive. What is more impressive to me is this. This is the chromium antimony ultramagnet grown on top of platinum antimony substrate by magnetron sputtering. This is RF sputtering, which typically is a rougher method for thin film synthesis, but it's very important because it's the industrial method, which is also used for MRAMs. The same thing. The chromium antimony across the entire wafer of a thickness of tens of nanometers is virtually defect-free. So we have methods how to prepare extremely high quality materials, which is the starting point for doing experiments and getting rid of all possible artifacts, obviously. Then we do either go to synchrotron, and we look at the spectra by doing angular resolve photoemission spectroscopy. Here, one thing that turn out to be extremely important, because if you want to see the spin polarization, and we also do spin polarized ARPAs, so it's not only the energy but also momentum resolved but also spin resolved spectrum that we can get from these detectors, you have to be able to prepare a single magnetic domain on your several tens of microns sample, because this is the size of the X-ray beam that they use. And so again, our colleagues in Nottingham, they develop a method, this is on manganese telluride, where they can prepare by patterning micron-sized bars and by field cooling the samples, they can prepare single domain where this arrow corresponds to the Nail vector in this altermagnetic manganese telluride, which is a several micron scale pieces of completely single domain material. And then you can do ARPAs on this, and you can have perfectly fantastically spin and angle resolved data. It is also, of course, a prerequisite for making the spintronic devices, because you want to have a single domain device which you switch back and forth for. So this has been already demonstrated, and these images, by the way, are direct microscopy images of the Nail vector done by photo emission electron microscopy combined with various X-ray dichroisms, in particular the circular dichroism, which is something that people thought, again, was only possible in ferromagnets, but in altermagnets we can have circular dichroism or anomalous Hall effect, these time reversal symmetry breaking effects we can have equally well. So what is imaged here is actually the arrow represents to the direction, the axis, but also the sign of the Nail vector in the altermagnet. And to the best of my knowledge, these are first images, microscopy images of the real space imaging of the full vector map of a Nail vector in any compensated magnet. And this is before, it's a free film before it was prepared in the single domain state, so it can show that you can have domain walls, you can have these topological vertices and all that, which is another topic in magnetism, which is quite interesting. But the remarkable thing is that this is a compensated magnet, and we can now image it, and we can image it down to the 10 nanometer resolution. So that's imaging, spectroscopy, and then you go to clean room and you pattern your electronic devices. You measure anomalous Hall effect, which people thought in antiferromagnets or compensated magnets was not possible. We see as big anomalous Hall effect as in ferromagnets. And you also can study the spin polarization of the electrical current by various methods. I can have our lecture on these methods, but these experiments have already, some of them have been already done. That's why I could claim that it has been already experimentally demonstrated.
Thank you. So, last possibility for question. If not, then thank you again. Thank you very much, and this is just like our typical learning class, so you can maybe find use of this. It's safe. For us it's safe, and probably it's a little bit radioactive, so don't eat it, but you can use it.
Thank you very much.
So thank you, and thank you very much for coming.